Hello everyone, I'm Cristina Rota, a data scientist at Deloitte Analytics and Cognitive in Spain. In this video presentation, I'm going to give you a brief summary of the solution that we presented to the 2020 Melanoma classification competition, which won the third prize. These are the points that we will cover in the presentation. I will start by summarizing my background. We will continue with a short summary of our solution. Then we will delve a little deeper into the training methods we used. We will share some important discoveries, and finally, we will present a simplified model based on our solution. Starting with my background, I am a biologist and I have worked mostly as an ecology researcher. In 2019, I decided to shift my career to data science and I joined Deloitte Analytics and Cognitive in March 2020 as a data scientist. As a preview, in this chart we can see our progression on the private leaderboard attributed to the different techniques we used. Our main approach was an ensemble of 9 models, 8 different efficient SIIM-ISIC image models built with various combination of image sizes, and one simple baseline model for metadata. To increase the number of training images and enrich its variability, we included in the modeling process the data from last year's competition. We also included hair augmentation in some of our models. In this section, we can see in greater detail the models we built. First, we built one simple baseline model for metadata, and then we built 8 efficient SIIM-ISIC image models. Among all convolutional neural network architectures, we chose the efficient net family due to its excellent trade-off between performance and number of parameters. All image models were trained using binary cross-entropy loss, label smoothing, Adam optimizer, ImageNet pre-trained weights, a learning rate schedule, and heavy data augmentation. The training epochs differ between models, as well as the training data, the user node of hair augmentation, and the image resolution. This table shows the 8 fitted image models with a particular configuration. 4 models were fitted only to this year's competition data, while the other 4 were fitted to both last year's and this year's competition data. We didn't apply hair augmentation in the last model due to computational limitations. Model training and predictions were performed in Kaggle's TPU kernels. Training time for a single model ranged from half an hour to 3 hours, depending on image resolution and the application or not of hair augmentation, with an approximate total of 20 to 25 hours for all models. Finally, we used ensemble modeling to get our final predictions. Our winning solution, which scored 0.9484 private leaderboard, was obtained by ensembling 11 models, our 8 own image models, the metadata model, and 2 Kaggle's public notebooks. In this solution, we decided to ensemble 2 public notebooks to our image models in order to add some diversity. However, a higher score can be obtained without using external data by simple ensembling our own 8 image models with the metadata model. This ensemble scored 0.9489 private leaderboard, but was not selected as a final submission for judging. Regarding the way we weight the different models, image models were ensembled with a simple average with equal weights to all models. The final prediction was then obtained with a weighted average between the mean prediction of the 8 image models and the metadata baseline model prediction. In this slide, we are going to introduce some interesting findings we came across during the competition that help us to improve our models. First, during the training process, we used hair augmentation in some of our models. This technique consists of applying pre-segmented real hairs into the images through mask-based methods in order to achieve more robust models. Moreover, our final models were fitted to the whole dataset without validation. This procedure is based on the idea that the more data you use, the more likely it is to have a robust model that generalizes well. Besides, the inference on the test set was made by applying heavy test time augmentation. With this technique, instead of directly getting the predictions of the test set, we asked the model to predict the same image a determined number of times, but each of them with a random modification applied to the image. The different predictions are then averaged to obtain the final prediction of each test image. Finally, we think it's possible that, in this case, having followed the keep it simple principle helped us get better results. Among all the single models we sampled, the one that obtained the best results was the one that we fitted with this particular configuration. This model was fitted without hair augmentation, although it was due to computational limitations, and it's possible that the results were better with the application of this technique. Our simplified model obtained a private score of 0.93 and took approximately 3 hours to train. To end this presentation, the whole Deloitte Analytics team wants to deeply thank the organizers and Kaggle for hosting the competition. If you have any further questions, please contact us and we will be happy to talk to you. Thank you very much.